Hello everyone, this is Zhengzi. Now I'm going to talk about my paper, Automatic Hot Patch Generation for Android Kernels. First of all, our motivation of choosing Android as a target is that there are thousands of Android systems in the world, but most of them are not up to date. They contain many known vulnerabilities. The table below shows the Android version distribution at the year 2018. From the table, we can notice that only 0.04% of Android devices use the latest Android system. The figure on the right shows the Android updates level for 500 million devices. By the time of October, about half of the devices only receive latest updates on May. It leaves a 5-month gap before they are updated. Therefore, there are a huge number of devices which are in danger because of lacking patches. In addition, if we manually write the patch, it would be very time consuming. Therefore, there is a need to develop automatic method to generate adaptive patches which can be applied to different Android systems to fix the legacy vulnerabilities. Considering the device performance and user experience, Hot Patch is an ideal solution since it does not require system rebooting and incurs little overhead. Specifically, the goal of our tool is that given a vulnerable function and its official patch, we want to automatically generate hot patches which has same semantics as the official patch. Here, we choose the function beginning to insert the hot patch, and we convert the official patch into a function input filter, which can block the value that can trigger vulnerabilities. Why are we choosing the filter rather than direct patching? It is because that in binary, it is easier to locate the function beginning, and in different legacy systems, the function beginning will not be changed, but the content of the function may be changed. If we want to insert the patch in the middle of the function, it may not be applicable across different systems. I want to emphasize that to ensure the filter will not affect the normal functionality of the system, we limit the filter to only perform read operations rather than write operations on the memories. So with this limitation, what kind of patches can be converted into filter? To understand that, we first conducted a survey of 375 vulnerabilities. From the table, we can see that sanity check patches account for the largest portion with over 40% of the total patches. It is a type that does not require memory writing operations. Therefore, we choose to convert sanity checks patches into filters. There is an insight from the survey. The vulnerability types and the patch types are different. There is no strong relationships between the two. When you are doing researches about the vulnerabilities, you should focus on the vulnerability types, such as buffer overflows. Whereas when you are doing patch analysis, it is better to consider patch types instead. Okay, after we figure out the goal and the type of the patch we want to convert, let's go into the detailed algorithms. First, I would like to introduce Wiki's fragmentation reasoning techniques. This technique tries to find what must be true in order for a post assertion to be true. Let's look at one example below. On the left-hand side block, there are some statements. X is equal to y and b is equal to a. We have put an assertion in the end, which is b is less than 0. Wiki's precondition reasoning will try to find the preconditions and can make b is less than 0 to be true. In this case, since a is equal to b, the precondition is that a is less than 0, so that b is less than 0 can be true. Similarly, on the right-hand side block, there is a function foo with a sanity check patch at the end. If we try to calculate the precondition of the sanity check, we can get the condition at the beginning of the function. You may notice that the condition itself is the same as the filter. In this way, the filter generation problem can be changed into a Wiki's precondition reasoning problem, which can be solved using mathematical transformations. There's a formal way to do the Wiki's precondition reasoning. If you are interested in it, you can search for the predicates transformers for more details. So now let's move on to the next component, function call handling. Through the weakest prediction reasoning, the algorithm may encounter function calls in the past. It needs to deal with them to get accurate results. First, there are functions that will be inlined by the compiler. To address this, we will import all the functions into the original caller functions before we start to do the reasoning. Second, there are some functions and we'll modify the content of the variables that we want to check. In this case, we will direct the reasoning to go inside the call_e function and summarize the changes of the particular variables. Third, we do encounter some cases whose function calls are nested up to more than 10 levels. Our method cannot handle this kind of situation, so we skip the function calls and mark this case to be inaccurate. Last, we have a special type of functions and can be processed through hooking. I will explain it in the next 2 slides. So besides the function calls, another thing that needs to be handled is loop. Because in static analysis, we do not know how many times the loop will be run. To process the loop, we also classify them into different types. First, if the patch is inside the loop, we need to rebuild the same logic as the loop in the filter itself, so that the filter can also be run for multiple times. Second, if the loop modifies the variable values, we need to use loop summarization techniques to get the semantics of the loops. For simple loops, the summarization can be very accurate so that we can solve out the condition we want. The third case is that loops does not modify any variable values that the filter want to check. In this case, we can just safely skip the loops to continue do the reasoning. Last, if the loops tend to be too complex, we need to skip it and mark it as inaccurate. Here, I want to mention that in static program analysis, loop and function calls are the 2 problems that need to be handled carefully since their consequences are unknown without running them. And here comes the last part of our component, which is the patch insertion point optimization. So what is an insertion point? In our paper, it is the function beginning. However, when the function calls another function, things will become interesting. Let's look at the example below. Suppose we have a function A with a vulnerability. We can always put a filter at the beginning of the function A. Moreover, function A has called function B. We can also put the filter at the beginning of the function B. By putting at the function B, we will have the equivalent semantics as we are putting the filter at the function A at the middle of function A. Therefore, to fix the vulnerability of A, we can either put the filter at the beginning or in the middle. We will let our algorithm select one point which have shorter paths to reason. Take the example on the right. If we are trying to do the weakest prediction reasoning from the patch, which is at the bottom of the function, to the beginning, it will pass 2 function calls and a loop. As I mentioned before, handling calls and loops may cause inaccuracy. It may not be a good choice. On the contrary, if we insert a filter to function B, the corresponding equivalent filter will be at the call of function B in function A. In this way, it helps us to skip the analysis of the function calls and the loops. The result will become more accurate. This is also the last type of function that we want to handle, but instead of handling it, we use them to achieve a better result. So let's move on to the experiment. We have evaluated the patch generation in 4 aspects. First, we have selected 59 official patches and let the tool to generate the filter, and we have manually verified that 55 filters are correctly generated. The remaining 4 cases are wrong because we have extracted the wrong semantics from the official patches. And second, we apply the patch to the kernels and measure the performance loss through Android benchmarking apps. We found that most of the time the filter will not incur performance decrease at all. Third, we want to test the robustness of the patch functions. we run the system for a long time with different apps and monitor it to find that none of the patched functions have resulted in crashes. And last, we also tested whether the generated filters are similar to human written filters. We employed security experts to learn the official patches and write the filters and compare them to the generated ones. The results show that 54 out of 55 patches are similar. The only one dissimilar case is because there are two ways to fix the vulnerability. The tool choose one way, while the human choose another way. So, and the last slide shows the future works and improvements. As we did this work, we found that there are many other places that it's worth to be researched on. First, we would like to generate adaptive patches directly at the source code level. By doing this, we can support more types of patches and fix more vulnerabilities. And second, if we still work on binary level, we want to enable the write operations in the hot patch. It can be dangerous, but it is also very helpful to fix more vulnerabilities. We need a program analysis to figure out which contents of memory are safe to be written and conduct operations on the safe ones. Third, we want to summarize the semantics of the patches. We found there lacks research in this area. By getting the semantics, we can achieve more accurate type classification method. We can distinguish the security patches from other function updates. Even it helps to examine the root cause of known vulnerabilities. Last point, our tool cannot handle the large and complex patches. We want to find a way to deal with them. Okay, that's all. Thank you for listening. You are welcome to ask questions.